Welcome to day two, guys. Hopefully, on day one, you had a lot of new learnings. So today we'll start off the first topic, which is functional verification on multi-chip reference designs. So we have three presenters today. So we'll take a break after each presenter finishes his slides, and you'll also have a lot of chance to ask Q&A, and you can ask it at any time. So just raise your hand, we'll provide a mic, and you can ask your question, right? So with that, I think we can get started. So our first presenter is Alok. He's been working at ARM for 7 years at Cambridge location. And before that, he has worked at Synopsys and NXP. And his focus area now currently is all functional verification. And also he has his bachelor's from IIT Delhi and his master's from Netherlands, right? Right, yeah. So with that, I'll hand it off to Alok and he'll take it forward.
Thanks, Vash, for the introduction. Welcome everyone for the session on functional verification of multi-chip reference design compute subsystem for hyperscalar SoC. A lot of heavy acronyms for Monday morning, let's say. Just beginning the day at 9 a.m. and with all these jargon. Thanks for your interest. Let's make it more engaging and learning for everyone. So please feel free to ask questions at any time. Just short note on the title. If you are familiar with the previous draft of the content, slightly changed. We're talking of reference design compute subsystem because reference design, the term, it relates to some offerings from ARM itself. And these are, you'll see in the material as well, this is what we use for reference for the conversation today. So that this is more relatable. So there's a slight change in the abstract if it's any confusion. Right, so this whole subject for today is organized as follows. First, I'll be speaking about reference design, compute system, and some general challenges in verification. This is followed by the multi-chip aspects and by Arul, and then we talk about emulation, how we use emulation for these kind of subsystems. Right. So reference design compute subsystems is just to explain the terminology a little bit. And so reference design, as I mentioned, these are subsystems that we offer as a reference. These are some design subsystem that you can that tells us the right configurations for a subsystem design for this domain. The offerings are in infrastructure as well as some Cortex-M based design for client side. Compute subsystem, so compute and subsystem. So it's something, the compute is, I guess it's pretty straightforward. Subsystem, so it's not a full subsystem, for full system, it's not a full SoC, it's part of the SoC, part of the system. And then we discuss the functional, the verification related challenges today. Just before I go further, if I can please just know the audience a little bit better. How many are we from academics? If you can just please raise your hands. Thanks. How many are from the verification in industry? Okay, and from front-end design, logic design? Anybody from the back-end design? Architecture, specification? Anybody from architecture, architect? Anybody from software? Okay, thank you very much. Right, so this is the outline of my talk. First, we talk a little bit about introducing the subsystem for the talk of today. It's called ARM Neoverse N2 reference design. It's based on a series of processes, the N2 series. Then we speak on the challenges in verification along these four main lines. How do we, the issues that we face when we want to define the verification space for a hyperscalar SoC. Hyper means a very large scalar. Yeah, so this is very large subsystem, the size. Role of design of verification closer. So it's not just verification and use specification that do how the design should cooperate or to solve this problem of verification. Compliance testing. So a lot of compliance is needed, starting from basics of protocols up to architecture and the domain itself. So there are standards for the domain, so the infrastructure, for instance. And it needs to be part of verification, often get not that focus. So we speak a little bit on the compliance testing and how, yes, so the verification executions itself, when you specified everything, when you have design, what kind of challenges are faced and how to make the right decision to solve those. And one of the conversation, a point that we see these days is about the usage of fixed virtual platforms for. So normally you have models for systems and subsystems. How can they be used for verification? What are their pros and cons, and how we can make use of those? And we do a recap on these conversations, and feel free to ask questions at any time. Right. So this is a block diagram of the subsystem on Neoverse N2 reference design. On the top left, you have what is called a processor block. So it involves 32 Neoverse N2 cores, and in a manner that is called direct connect, the dynamic shared unit. In a nutshell, it does not have this part of the design does not have level 3 cache. So the processors have their own cache, L1, L2, and then they directly connect to or with a minimum logic around them, they connect to the interconnect. Yes, a lot of components are shown here. So this we have our Neoverse core, and then you have blocks for power control. You have blocks for interrupt communication to the processors. The system sends interrupts around using message-based interrupt handling, so that when they reach the CPU, then they need to be transmitted. So you have interfaces for that. And a lot of details not shown here, like you need logic to control clock. You may have interfaces you can provide to the customer for introducing sensors, so that you can have better control on the power and talk the rest of the system effectively. This talk connects to the interconnect for the whole system. It's called, I guess, coherent mesh-based network. This is CHI terminology, request a node with CAL. CAL is nothing but like a MUX. You have then you have various other interfaces, not only from some to communicate different parts of the system, as well as internet trace. Yeah. This block represents the unit that handles the interrupts, HICC 700 generic interrupt controller. Yes, it is a distributed interrupt controller. So you have other blocks called distributor and distributor interrupt translation services. ITS is nothing, just like MMU does for the address. Here you have a similar unit doing the same for the interrupt. And you need to be able to debug the whole system. So you need infrastructure that can tell you what the CPU is doing, what the CMN is doing. So you have traces from whole of the system going towards that block shown in the top right. And then it dumps the information in memory or trace port can take that data, and you can visualize what's going on. So it's called the debug block, again, represented very high level. A lot of details goes. It's a mini subsystem on itself, the core side components distributed in the whole subsystem, and then finally talk to the interface units toward the JTAG debugger and trace ports. On the top right, what's called a MSCP block, manageability and system control processor. The Cortex M7 based. small subsystem within a subsystem. So you have two processors indicated here. One's for the manageability control. So your system needs to record it, a lot of events. For instance, if errors are happening in the system, too many, then somebody needs to tell to the rest of the SOC that there is a pertinent issue. So that kind of functionality is provided by this MSCP block, MCP block, and then you have SCP block, which is system control processor. As the name says, it does a lot of control part for the subsystem, with like clock control, power controls. Again, it talks to the rest of the system using what's called message handling units, and a lot of logic goes around that block. That's another key part of this hyperscalar, one subsystem of hyperscalar, is connectivity towards the I/O, towards PCIe, for instance. So you have TBU, transmission buffer units, and translation control units. The MMU components shown here. Your PCIe related root ports talk to the rest of the system using the interfaces here. They are translated using this MMU and go to the rest of the system. A very key component part of this. You need logic for providing the different bifurcation, like ×2, ×4, ×8. So all that complexity is hidden in this block. Similar is the ITS, as shown here. You need ITS to translate interrupt coming from the rest of the system coming to this block. Then you have what's named as peripheral block. It provides things like watchdog, timer, UART for the CPUs. And then, last but not the least, it's a CMN, the coherent mesh network, CMN 700 in this case. Provides, I think it's about 6x6 mesh. So you have the whole interconnect is mesh-based. You have nodes talking to each other, and there's a 6x6 matrix, I believe. And also provides connectivity for the multi-chip using the CML coherent multi-chip link symmetric multiprocessing protocol. I believe that's the full form. It's not C6. I think it was attempted to be part of C6 version. I'm not sure if it's already there, but yeah. So you have standards. So this CMN provides connectivity and standard toward so that multi-chip related connections can be made. And finally, you need a lot of DDR, high bandwidth memory to provide all the computation memory for the computation. So here you have, I think this is DDR5. It provides any two configurations. So if you look at this picture, then it highlights the key part for the what's called hyperscalar SoCs. You have a large number of processor count for large computation. You have memory connectivity. You have connectivity to I/O or accelerators using the I/O block. And multi-chip is another key part to provide further high computation that's provided by the CMN. And in order to achieve all this, you need the interrupts, for instance. You can't have wires going through the rest of the system. It needs to be a message-based interrupt passing, so that itself is a big piece of logic. And of course, you need to be able to debug this. So you need debug connectivity towards JTAG and trace ports, and a lot of components not shown in debug are distributed throughout the system. These details can be fetched from furthermore details can be fetched from the links below. So in a nutshell, you have a subsystem with a large processor count, large complex IPs, and a lot of functionality goes in making such subsystems. This slide depicts the multi-chip aspect of this. You have two main topologies depicted here. You have dual chip, where what I described in the previous slide was for the single chip, let's say, and then you can have multi-chip topologies derived using that, connected to each other from using CML, SMP, as I mentioned before, or CXL for the memory expansion. And then you have two flavors mainly, dual and quad, that are supported for this subsystem. Right, so we go multi-chip detail later on in the next session, but just in a brief, when you have this kind of topologies, you need to have possibility of interrupts going from all the way from the other part of the system that you have in the previous slides to other subsystem in the other slide. So interrupt, you need to be able to trace from other chiplets using a JTAG, probably connected only through one. You need to be able to have, you should have coherency nicely implemented in this kind of subsystem. So you already have a huge subsystem, large number of cores, IOs, which need to be fully coherent. And then on top of, you get 3 more instances of the same. So all these essentially become part of your verification space, which is a complex area. You need to be careful defining those and execution. So that's a separate track itself.
The difference between second and third, they look almost similar.
So you mean these two? Yes? Yeah. So here we have 2 chiplets implemented in same package. Here you have separate packages for all. So the connectivity will be different, in some of those. Right. So now we talk about the verification. What this all poses issues for verification. Well, what are we talking about? So if you just pick one, how it is defined in public domain. Functional verification in EDA is a task of verifying the logic design that conforms to specification. Functional verification attempts to answer the question, does this proposed design do what is intended? This is a complex task and takes the majority of time and effort in most large electronic system design projects. Functional verification is a part of more encompassing design verification, which besides functional verification considers non-functional aspects as well, like timing, layout, and power, and potentially more. It's a very nice description. Nutshell, yeah, it cannot be more accurate and precise, I presume. So the keywords I highlighted here, it's a complex task. It takes the majority of time and effort in most design of electronic systems. It also needs to take into account non-functional aspects. And yeah. Right, so I mentioned before we talk on 4 tracks. So this is the first one. How do we define what we need to scope for verification for such a system? So you got the specification, you got an understanding of the standards and everything, but you need to put what you want to implement so that everything can be nicely, like it doesn't go forever. Time to market is also important. So you need to have a strong, robust verification plan. And how do you go about defining that when you start for a system like that? Right. So when you go about doing that, you need to have large set of large sources of information for that. You need a product your requirement specification. It can be very high level as well as detailed. You will have, of course, high level what your system needs to achieve, which protocol, which interfaces. It also can go down to the level of defining precisely what kind of configurations that are needed in the market, in the industry for that. And yeah, those details need to be part of your verification plan. Then, of course, the system architecture itself. There's the next level of detail where the PRS is broken down into what can be designed, how the architecture would look like, which component will be used, how they will talk to each other, what will the memory map look like, what will the interrupt map look like. All those, again, they are these are documents intended to define design, and so it's not that you can start executing straight away with these. You need what is called a design specification. What this high-level architecture when you want to write RTL, when you want to write design for that, how it will look like, what actually, which wire will connect to what, how you can configure, what will be the data width. To those details, they are specified here. Now, a lot of things can be, when you start from a high-level document from here, you go from there, you go from there. A lot of details may not be specified in here or even there. And even in design document, there may be things like still not defined to the full detail. System architecture may address the product requirement, but it may still leave scope for what an implementation or designer can choose to implement. Can make some design choices for using when they want to address the PPA targets. And then you also need standards. I mentioned before, for instance, for this kind of application, you have standard called SBSA, server-based system architecture. You need to make sure that what your system is designing will eventually comply to those industry-based standards. Performance requirements, of course, you need to ensure for the specific use cases, the required performance will be met, and those will pose some test points. Of course, the non-functional. I told all your planning needs to be achievable within the required time frame. There will be views, deliverables, which are non-functional in nature. For instance, used for automation, like XML views for the whole system. There may be, I asked for somebody from backend, so there may be requirements from the backend team that your design should be possible to be digested by EDA tools. Not always possible unless you take care of them in this part of the step. So and then it becomes part of verification as well. So all these information needs to be digested by what you will call a verification plan for the rest of the project. And the challenge here is with all these complexities, how do you define a verification test point that can be understood by everyone and can be executed and meeting the required time frame. So yeah, it's a complex activity and needs to be given fair amount of time and attention. Then once you have done that, your verification plan may include some of the points mentioned here. You have let's say layered complexity of test points. Your design is built based on small design units like CPU, your CMM, interrupt controller. They should be fully verified. That's probably the fundamental assumptions you're making when you're designing a system. Your system should have, you need to boot the system. There may be requirements on the boot itself. Clock and reset should be successful. And then you have another layer of testing, memory map, interrupt map, power control. These are basics, bare metal testing requirements you should achieve before you go to further complexities. You need to make sure all the data paths are working. You should be able to debug, send traces from one point of the system to another in different states of the system and still successfully debug that. You have coherency requirements. You will have use cases before you go even to performance. You need to ensure the security requirements are met, particularly as these are very highlighted these days. And then, yeah, always bring up as your primary. Should you do everything in RTL? Should you? Sorry.
Question for the reference design. Could you just say a little bit about what the intention of the actual reference design was, who you expect to use it? Is it virtual or is it also physical? And also, does ARM sell it, or are there warranties tied to it? Just because that seems like that would color a lot of this.
Yeah, sure. The reference design are the topology that I mentioned is RTL, and there are models as well. And it gives you indication of what PPA requirement you can met with that kind of configuration. It details all that, and it's downloadable. I believe RTL itself is you can download and use it. Of course, there will be legalities around the usage of it. It's not meant to be taken to silicon. It's just for the reference design. but it tells you you can use the RTL of all the system mentioned there and study it. Yes. No.
Is so in last APM ARM partner meet, we have announced Subsystem as a product line. So there are some of the self subsystems available where partner can go for their SoC using them. So, but as Alok said, it's not like it's not getting into silicon, or we don't have a test chip for it. But there's a product line announced in last APM for all the infra subsystem for now. Infra is the data centers and servers lines of business. And in client side, we are yet exploring. Okay, but addition to the RTL, we have implementation guidelines and all sort of guidelines available along with it. If someone want to use that subsystem and get into product, they can do so. But it's more sold along with the IP, these reference designs. But subsystem itself is a product line, which ARM announced in last partners meet.
So you can download RTL simulated. You can download the model of this and simulate it. That's all doable.
So what you're verifying are the work products that are actually being sold as a part of the product. That's the verification.
Yeah. So this is the outline is showing that what kind of verification you may need to do that to take it to silicon. So there are, of course, the quality will differ. So this is an example of a test point. So in this, I mentioned it's a increasing complexity, and somewhere in the middle we have what's called memory map, intermap, and power control. So let's look at what a moderate or simple test point for something like this looks like. So yeah, so let's take example of memory map verification. So what is memory map? So you need to be able to access all the locations from all the sources of transactions, or legacy terminology masters can send their transaction towards their destination or slave in legacy terminology. You need to be able to prove that it works before you can do anything. So you have, if you look at this kind of subsystem, you had 32 cores, you had interfaces coming from for the I/O part of it. You also have what I did not mention was expansion interfaces. So you have rest of the system on chip can access DDR, for instance, or access other points using what is called expansion interfaces. You had debug and interrupt controller components, and then from the endpoint you had DDR memory here, and you had watchdog timers and those components. So it's a significantly large number of masters or the places where the transaction can start. You need to make sure that you have all the memory regions, and within memory region you will have a purchase that are all accessible. And these regions of purchase can have specific behavior which may not be generalized, that valid for all. You may have reserved locations which it should not access, and there will be behavior associated for reserved locations. And then the data part itself will have its own functionality. There will be security attributes, like in secure mode, the transaction will have some behavior we should not be able to do the same for the non-secure. And with the latest, the RME extension, you have even more security attributes. So that's only the specification of it. When you start executing it, you may get into the situation where your data path itself is, after source, you have data path which is programmable. You may need to set it correct so that your transaction can reach the next level of design, system interconnect, let's say. And then after that as well, there may be security checks or other translations where to reach the destination, and the same way around. And doing that for such a subsystem, for one test case itself can be quite time consuming, and a lot of understanding is required before you try to code and debug such a transaction. So challenge here is, it's a subjective interpretation. It can be moderate. So even if you take it as one of the basic test cases, it can be significantly complex activity before you go to the making some use cases that on such a subsystem. So the question is, can you utilize formal verification techniques to?
Formal verification, or is there any software or tool where we can do all this?
Right. So there are attempts to automate a lot of things around, let's say, memory map as an example. If you look for many EDA vendors have where you can specify a lot of things on Excel sheet and then you can dump some test cases. But once you some of these there are tools. So to answer your question, for instance, let's take this as an example. There are tools, but when you start applying that, are they generalized for valid for all the test cases? Just to make the right setup for something like that. So tool is there. It has prerequisites. You need to provide information in an executable manner so that the tool can process it. It may dump out a test, which may need to be modified, fine-tuned to suit your test environment. So there's a lot of, I would say, overhead. I don't know if there's somebody from media here. So tools are there, but success of those depends a lot on what system you're using. Is it simple enough? Is it structurally enough so that you can just, out of the box, dump your test case and execute it? So is something like this, you may end up hitting a lot of issues, a lot of fine-tuning for the test case that may prove that the tool itself, you may better do it by hand and repeat the process rather than setting a structure. So you need to look at maintainability of your verification so that you can use it in your next incremental development. So when you take all those into account, may be successful, may not be successful, depends on your size of the system. And again, you can use a tool probably to get a start point. But with the tool, you expect return on your investment, right? But if you have significant amount of overhead to getting to a setup point, we need to pull into a lot of information from the IPs or from the system memory map to generate a test point. You need to think, is your tool, is that the right approach? Sorry? I'm talking about simulation. Yeah. So yes, so there are tools around it. Success of those is subject to a lot of your system, your goal, your test cases. For something like this, my observation would be that you may need to fine-tune and change that generated test kit itself to get to a state where it can be used. Yeah.
If you try to use 10 test cases, what is the percentage, like if 5 test cases are good or above threshold? So can we say that it's a good verification?
Again, you need to see about your maintainability of such. So suppose you do 5 out of 100 test cases are doable by the EDA tool. Is it worth the investment? For
5 out of 10.
Let's say, yeah, so 50% test case, if they are automatically generated and executed out of the box, it's a reasonable approach. But still, you need to think your incremental, is it future proof? And how can you trace your requirements? Sometimes, if you are generating design as well as test from the same source, is it a correct approach? Can the mistake percolate if you are using the same source of information? If you need to think. But if you're saying you have a setup where 50% of the test cases, something like this is achievable out of the box, I would say it's quite a good hit. You need to make sure that your IPs are interoperable to each other. Now, yeah, so for example, you have let's say relatively simpler compliance issues, different version of the protocol. like Chai versus Chai-F. Chai-F introduces what is called RME extensions. Axie-4 versus Axie-5. Axie-5 introduces a lot of new functionality, but you may see that some of the structures, some of the signals are static. So how much do you need to worry about interoperability? But can be an easy issue or difficult to solve. You need to make sure that your the functionalities are provided by different IPs are interoperable. For instance, if your system requires that your error generated when you have a parity error at the memories, then it generates an interrupt towards a processor. Is the design using parity checks? The IPs, do they implement all that error generation and propagation? You need to ensure there may be requirements from one IP to the other regarding timing and performance. Some IP may need to implement register size with just the break the data path and put some registers so your timing can be met. Should it be done in IP1, IPA, or IPB? It may impact some of your testing. So the challenge here is, before you go about hitting your verification execution space, have you looked into these aspects? Because if you start hitting this late in the project, you may not have enough time to ensure these. So interoperability, again, probably one of the items which can easily be slipped as in design considerations, but need to be given careful attention. Ensure that you have thought enough about your scenarios that you want to system to prove, enough of the use cases that you're designed to be used. But again, the problem here is how to go about it. Do you want to be a fully yeah, so if in this example, for instance, you have one of the IPs can be taken into three states. Let's say one is just execution of the code. Another state is, let's say, it's powered down. Another is, let's say, it's being debugged. And then similar for the other IPs, do you need to have proven that all the combinations work? So is it a full cross of all the states, or do you need to have a subset, a meaningful set of states? You need to have a given, so of course you need to have this. You can't do a blank.
Suppose if the combinations will become combinatorial, then what we have to do? We should do any. Suppose the combinations become combinatorial, that means they become NP-hard. Then what should we do? If the combinations are too many, so what we can do about
So
should we do a brute force way of verification, or should we do any optimization based heuristic optimization based verification?
So for the scale of this, so you can do your brute force approach on a smaller subsystem, but for the scale of this is not. So it will break your time to market constraint for sure. If you have 32 cores and CMN and IO, you will be forced to go to a meaningful discussion with the architecture specification, design specification within your verification team to come to a meaningful set that are useful use cases for such a system. Some of the use cases may be just meaningless, or there will be preconditions before you bring the system in a state. You can't just power off one, you can't just power off the other without doing the first one or something. Yeah, so you may need to define and then put some constraint that give you some subset, and then you still need to refine using approach with the right people. So again, the problem here is defining a complete set. One would say it's easy to just do everything, but your other requirements will come into picture, and you will certainly not be able to achieve. Okay, then we talk about the role of design itself. You can't do a design and verification in isolation. They need to talk to each other. Because one of design choices can greatly affect what you want to achieve for verification. Right. So what we just saw, what does it take to implement a design for something like that? You need interconnect not for the core CMN, but for the other part of the systems. You need domain bridges. You have clock domain crossing from different part of the system. So you need to implement bridges or implement clock domain crossing. In this case, we have IPs to do that. You need to plug in components to provide traces. For instance, CPU and interconnect, they will have sources to capture trace and send it to the debugger. you need to you need to integrate the IPs which achieve that. You need to have clock generators in different part of the system. You need the RAM and ROMs and other peripherals like also watchdog, timer, UART referred as peripherals. You need memory controllers, in this case third party, or you can have your own. Of course, you need the CPUs. You need a CMN, in this case CMN 700. You need a processor for system MSCP part of the design. You need interrupt controller components. It's a distributed interrupt setup, so you need to have plugged in different components of your interrupt controller. You need to have the memory management unit. You need to have the power control infrastructure. And yeah, like 700 again, flavor of the interconnect. Right. So in summary, this is a huge design, and when you have such a large design, it brings challenge not just to you. If you want to implement test case, you need to understand how all of these IPs work. So you need to. So there's a part of this to understand the right functionality for all these IPs, or you need to set it up your verification plan as well as execution to tackle this, because this is too much functionality to digest to achieve the desired goal within desired time. So you need to address that. A lot of people are from the verification. This itself can pose a significant challenge for the EDA side itself, particularly for the backend side. You need to look into the configuration space. We can start from the product requirement mentioning you need to be able to support so many configurations. You need to be future-proof to be able to support some more CPUs, not just N2 in this case. You may need to support different data width, different core count. So all the requirements can come up to. So first challenge is how to define architecture for that. Suppose they have done that. This is configurable. It's a problem of implementation. Design can do that as well. Some automation can be set up to generate RDL. When it comes to verification, you need to think. Verification, so how you can make can you prove all this functionality work for one configuration within reasonable time? So again, it's about doing everything within the desired time. You need to make sure when the design is created, you are using the right configuration. For instance, your system requires that NPAM function as a memory part, performance and monitoring should work. Simple requirement. But that means that functionality should be enabled in the relevant IPs. Is it done? You need to take into account before execution. There may be requirements of performance and timing. Should you do that in simulation or static? There could be tools to achieve that in a static manner, which is more efficient. We need to think about all these things before you go about execution. The configuration space can be huge. Each of IP is quite complex and provide the user a lot of flexibility so that they can fine tune depending on their PPAs. All of that configurability need to be contained in a manner that you can verify. For instance, either the configuration can be fixed. For instance, number of CPUs can be only 32, not 64 or otherwise. Or it can be made configurable. Customer can change it. So it can, when you cross all the configurations of different types, it can be a huge configuration space. Again, the same problem as we discussed before. Should it be a brute force approach, or should you look into configuration space and derive meaningful configurations that you can achieve within the within the team you have and within the time you are given? So, and then of course you need to think that when you code test cases for that, you will be implementing firmware to program the different parts of the system. It needs to be configurable. For instance, if the number of interrupt sources is changing, your test case should be able to understand that in an executable manner. So it poses for challenges for execution. And you need to think hard. You need to look into the future. Will you be able to sustain all the different configuration within the time frame you have been given? So that's a huge challenge. Not easy to do. Often you may end up doing only one or two configurations.
The decision of simulation was a static check.
Right. So this is a so I don't know if I agree with the question is, can we have an example about should be of a simulation-based test or a static check. So the example used here is of configuration checking. So configuration is nothing but Verilog parameter values. For instance, data width, address width. It is given a specific number. It's easy for implementation to just connect, provide that possibility to the top level of your design where customer can change it. So they do that. But the challenge here is the para configuration that you specify reaches the endpoint where it is implemented. For instance, at the top level, I say that the number of UARTs can be 2 or 3. But at the top level, you expect. But that value has to reach 4, 5, 6, 10 layers design underneath the design. If that is the case, you could think I could put up a simple formal-based test case where a value is correctly connected or a value is correct. These are static. You're not simulating anything. The value is just correct. Now, what is the effect of that parameter? Is it taking the right effect? You could argue that it's a problem of the IP verification. When you're making a system, you expect your watchdog to work when a value is changed. So you could make that assumption. But if the value is affecting 2 IPs, you need to think that do I need to simulate and prove? For instance, MPAN can be enabled in CPU and interconnect. But are you achieving the desired result for the system? You need to simulate. Although you can check using formal verification that value is nicely propagating through design hierarchies to the endpoint. Yeah.
Subsystems and other stuff. So, at what application level do you think that physical verification fits in? Simulating some of the analog blocks with some of the subsystems, or maybe at IP level, what?
Right. So at least in this, so this is let's say referring some, not in this specific example. You are, let's say, if you want to use what's a PLL model, there will be consequences for simulation time if you start using analog models. So you may need to do a lot of tricks, simulation optimizations, for instance, black box, certain part of the design. So you may end up doing a lot of things to speed up.
But those are done at mostly at IP level.
IP level, yes, that's an IP level problem, I would say.
One question I have. We talked about all the parameter and interdependency on model to model or IP to IP in a subsystem. Is there any way we can get the coverage on the parameter combination that's supposed to be tested?
Yes. You need to implement. You need to put some coverage points. So it depends on your the problem itself. Is it a big configuration space that you want to provide, and then you want to see that you have proven that it is there in a system level coverage on configuration itself? Yes, it can come into picture. So you need to put what's a functional coverage point, the typical system Verilog FCOV. It can come into picture. Yeah. Does that answer the question? How are we doing with respect to time? Yeah, so fundamental assumption you should make and stress that your IPs that are being used are proven. You don't want to end up doing IP verification in a setup where you have such a big RTL space and test bench itself to prove that the IP works, because your system is only as good as your building blocks. Even a FIFO or a clock domain crossing implementation can break your system to a great extent. So the message here is you need to be absolutely sure that your building blocks are fully proven, because the rest of the that's the starting point for the further complexity that you will hit in simulation. Right, this is an example when design and verification need to talk to each other. You need to have a design that can be verified. It can't be other way. So you have two implementation of same thing. Suppose you need to implement three functionalities in part of a subsystem. Your ABC, let's say one is providing peripherals, another is providing memory, another is providing part of the interrupts. So you may have situations where these building blocks are already present, or they need to be implemented from scratch as part of your project of the system. So suppose these functionalities are being built from scratch, and you get a proposal that these functionalities will be implemented in this manner. There will be three different blocks, and they will be designed like in a manner where some IPs may need glue logic. For instance, a protocol conversion might need, because of various considerations, for PPA considerations or future compatibility and so on. So when you are going for the system level verification for something like this, is this a better approach by the design, or this is a better approach? I don't know if somebody wants to give it a go. So as part of verification, you will of course need to make sure that your previous assumption is valid, that the IPs are bulletproof. And that means it favors this kind of approach where you can have units separately verified in a UVM-based environment or something like that, where they are nicely proven completely. But the problem here is glue logic. You may need to do that you need to target that in your system verification. And there is a connection part of it as well, not very highlighted. Like these three are talking to system interconnect using, probably that needs a separate IP itself. So you are dealing with the unit level verification for three different IPs. Then at system level, you need to target that this is bulletproof. And then you need to make sure that the various cases of this part of design are also proven. For instance, you may like to see that when transactions are going from this block at the same time, can still successfully reach the interconnect. So still, when you think about all that, would you still prefer this approach or that approach? Given that it's all being built from scratch. This problem may be difficult to contain at unit level. You have a lot of different functionalities that you need to verify, but it may be simpler for the system part. On the other hand, suppose when you are starting a system design, then if these are already proven blocks, designer may still like to use these blocks because they are just more familiar with that. They may not like to change few things. So before they go into that, and they may like to implement that separately because of various reasons. And they may still need to connect to the system using internet, which can be existing IP itself. So it can be a favorable approach for design, but you need to get into conversation because suppose this block is also pre-verified. All you need to do in system verification to ensure that use cases and operability is maintained through this, which is a much simpler problem in this picture. In this case, if it is fully proven block or not. So you need to make sure that design choices are suitable for verification, and you need to do that early in the time where things are being specified. Right, compliance testing, often not given sufficient attention. So that's one of the reasons I brought it here. So what is compliance testing? You have different compliances. One is simple protocol. On the IPs, one is designed for AXI4, is talking to AXI4. They are connected correctly. Then you have IP architecture compliance. For instance, your interrupt architecture assumes something that if it is distributed interrupt architecture, that the correct component is present at the correct memory location. Your power control network assumes that different parts of the different IPs that are implemented to implement the power control are again present at the right memory address, and they have the right functionalities which your IP architecture assumes. And then you have system architecture, the compliance. It may be that that your system is expected to provide a default behavior or a fundamental features. For instance, interrupts for certain part of the system can be given a fixed connection to the CPU so that the software can start being developed. Because then the model is implementing that interrupt from your one point of the system will definitely go to pin a specific value of the CPU. So they can start implementing the software much earlier in the time. And when you ensure that your IPs can talk to each other, then that means you can pick IPs off the shelf, connect them. Verification also, it's less headache. You don't need to prove a lot of things. And then a lot of things can start early, particularly for the software development. And of course, it gives a experience out of the box. Again, when the customer is expecting your system for server will be based on server-based system architecture compliance, then they are already building the software. When you say that your system will be available 1 year from now, but they are already starting based on that assumption. So it's all for good. It helps to achieve faster time to market, but of course it brings you additional points to be proven in the verification environment. To give an example, this is the list of compliances that this particular subsystem adheres to. You have IP architecture compliances for the interrupt control. As I mentioned, you need to make sure that all your IPs are using the CHI, so coherent hub interface specification, particular flavor of that. You have a system architecture. So this is a key one, server-based system architecture that you need to be compliant with. You have a base fundamentalism that you are, AXIAs in this case. You have other IP like SMMU, core site-based system. The core site, what is core site? So these are the debug components present in the rest of the system to provide you debugability. That all this infrastructure adheres to what is called CBSA and debug. But how to achieve this? So when you have all these requirements, some of them can be achievable just by construction. So if you are picking up, let's say in this case, ARM-based, everything is ARM-based, your power policy units, your interrupt control, everything is, of course, complying to its own standards. You may need to prove that they are nicely communicating to each other using memory map verification, for instance. You may need to hook up protocol checkers and coverage items, for instance, for different parts of the part of the design implementing protocol. Suppose an IP is CHI-E compliant and connected to an IP which is CHI-F compliant, but you are not using the features of CHI-F in a particular version of the system, and the signals are tied off. Should you just, or how will you ensure it's correctly connected, just a tie-off value, or you want to simulate it, like the question that was asked? You may need to hook up a protocol check and prove that it works. You may need to you may need to do some coverage closure. For instance, if there's a glue logic between protocol conversion or AXI4 to AXI5, just an example, then you need to make sure that that glue logic works. The protocol is not broken. So you may need to hook up a protocol checker. You may need to hook up some functional coverage around it, and you may need to execute the architecture compliance. So as I mentioned, there is a server-based system architecture requirement. So it basically gives different levels to your system depending on functionality it implements. It could start as an IP version. So are you using the right version of the processor? Are you using the right version of the IPs? That gives you one level, and then you go to higher complexity. So is your design based on a fundamental base system architecture? It's called. On top of that comes the server requirements. You may have requirement of MPAM implementation. Your design should be reliable, addressable, serviceable. So RAS testing, it's called. So you have different levels of requirement, and based on that, it gives you, I think the latest one gives you up to 7 SBSA. And it's generally helpful if you have already a test case which you run, and if all the tests pass, it says it is compliant. But there could be. So depending on which compliance, protocol compliance, or so the challenge for something like a system is if you want to prove that IPs are connected. So there is no, let's say, one approach for everything. If there is a glue logic in your data path, one would recommend that you hook up a protocol checker. But when you do that, your challenge is that you are ensuring that all kind of transactions are passing through the data path, so that right protocol check has been triggered. The problem that also comes with this simulation time will significantly increase if you have a UVM-based environment. Sorry? You could start from the basics, like when you are defining the verification specification, and you can look at design carefully.
But is it automated or is it manual? Yeah. Is it automated or is it manual? Like if there's a compliance dependency. So is there an easy way to do it, or?
So for something like SBS, as I say, there is an easy way. You have a compliance test use implemented in, I think it's C. You can download it and execute it. That's the easy way. But once you have to implement protocol checkers to prove that protocol works, there are a lot of considerations. I would say it's not the easy way. Manual checking, the bare minimum you can do is ensure that the right signal is connected to the right destination. But you may need to simulate as well. And you are assuming that your design does not have implemented something else before it. So you need to make sure that you're picking up the right starting point of check to the destination, ensure you know. So at least you can do that the right signal is connected to right. But sometimes you simulate and see the IP one is assuming something else. The timing can matter. You may not be able to connect one protocol to another to the same protocol directly. You need to have a register slice before that. So there are a lot of considerations before you. So something like ACS, easy to mention. That proof gives you a lot. There are complexity there is, for instance, SBSA in this case give you compliance for the whole system, but your subsystem does not implement the whole functionality. For instance, PCIe related requirements, your subsystem is not implementing PCIe because it ends at a ACE protocol. The rest is up to the more implementation or your SOC designer. Are they doing the necessary requirement checking? If not, how do you go about doing it? Do you need to prototype it? So some of the considerations are there, but still you can address a lot using. So automation is, well, so these are executable test cases are there, for instance, something like this. You don't need to do any automation there for that. But otherwise, you need to look into detail for that. Right, so this section about execution. So this is what typically would be doing when your specification is ready. You create test cases. You make it part of regression. You do failure analysis. You do coverage analysis. Often design is breaking, bug fixes, RTL update, and then again the same cycle repeats for a significant part of the verification process. The problem here is what's the length of this cycle? It can be very slow. It can take a lot of time because system simulation is huge. It's millions of lines of codes. It can be very slow. UVM gives you a lot of functionality, but it doesn't come for free. There are a lot of overheads associated with the UVM. You may need to fine tune those parts. Before you get to a meaningful test case, you may need to do a lot of setup. You need to boot the CPUs. You need to program your CMN that the right source can talk to the right destination. You need to program your interrupt controller that interrupt from the source can reach the right destination. And then you talk about doing some meaningful test cases. You have your design and test benches are huge. The EDA can break, as simple as that. I've never seen a project where EDA did not break, at least for a few times, both in RTL verification and backend design. There could be design choices because of that. You need to bring that. So signal names can change, design hierarchies can change over time. You need to make sure that your verification is foolproof for that. Just that simple test case can be very complex. And to achieve your meaningful test, for instance, a secure transaction from a CPU has reached the endpoint securely, and you got the response securely. It can take quite understanding of so many IPs in the path, a lot of knowledge to create such a test case using C or whatever automation before you can look all that in your simulator and say that it's okay. So it's a very slow converging process. you may need to be requested to make it fast.
Nowadays, we claim that we have AI and machine learning implemented in their tool, and they have a lot of scalability. You can run your regressions across a lot of processors, a lot of machines. And do you use some kind of machine learning algorithm tools to, to give you a speed up of the kind of design that you are verifying?
So basically, what's the applicability of machine learning in reference design subsystem verifications? It's fair to say. Because IP level and subsystem level problems are different. So machine learning, to make a meaningful machine learning as a solution meaningful, you need to train the models. For that, you need data.
That's what I'm saying.
Yeah.
So when you run regressions, right? Your system is same, right? Only thing is, your test, the test vectors might be different, right?
Yeah.
So that's what I'm asking whether whether you use tools, and does machine learning really helps?
Yeah, so that's why I'm coming to. So in order to make machine learning a meaningful, viable solution, you need to train the models.
Right.
For that, you need a lot of test cases with sufficient variation among them. You need to make sure your design it's triggered to sufficient extent, and the model is trained then.
Right.
For something like this, in order to make machine learning a viable solution, you need to have a large number of test cases, so that the machine can tell you about the next problem. So what is the next problem? Is it configurability of the subsystem? Let's say you want machine learning to use so that it can tell you a configuration is verified. You don't need to verify that configuration. In order to have a model that can tell you, you need to have a huge number of configurations already so that it can tell you the next model. So let's say 100 model you need, so that it can talk about the 100 first. It's very difficult to pass through a large configuration space to train the model. As I mentioned, so time to market and all that. It's very difficult to have a large number of training points, data point for a problem like this, in my opinion.
In some company, if there is an experience which is already built in some company and are testing it from long time, so why can't they publish a data set with these verification parameters so that it will be useful for?
So the explanation is still valid here, right? Let's say if you get that, okay, these verification subsystems are verified these parameters, and then somebody can take those parameters and change one. Yeah, but again, do you have sufficient data points to have a meaningful model? That's a big claim and big problem.
For verification, improvement, and enhancement, but we are talking about subsystem where it doesn't have that many configuration or that many data points to build a successful AI and use it for the future subsystem. That's work in progress. But if you go for IP or any other verification, there we are successfully using ML. We have explored ML on system level stress side, where we are using these random instruction sequence tools, RIS tools, and then we see the effectiveness with the data which we have, whether how many such confs you use, the test configurations you use to get a design saturation, for example. So yes, ML is being accepted. In case of subsystem, what Alok was telling is, we don't have enough data in terms of how many configurations we have tried so that we can build a successful ML model. Yeah. Yeah. So there's a difference between hardware configuration and software configuration. And here we are talking about hardware configuration, which is very, very specific to a particular product and very, very design specific stuff. So, once it is productized, this is we are talking about subsystem level, correct? And these are reference to achieve a PPA, which is power performance in area. If you connect the system like this, if you configure the parameters like this, you're going to achieve a certain number. So this is very specific to a product, and unless a product is in the market or these data can't be released, and we are talking about verification effectiveness, and you are talking about the details of a hardware configuration. If we talk about verification effectiveness, we need that many test cases, that many data, that many combination, and the results of it to build to give the weightages into your AI model to say that out of 100 test cases, if you run 80, you're done. Correct? So for that subsystem scope of this presentation, we don't have that enough data to really benefit out of it, but that's a work in progress.
Yeah. I'll take 7 more slides, I believe. I'll try to conclude it in 5 minutes. Once you have all these problems, you need to make the right choice. You have typically either a C-based testing, because you have processor, you need to execute the code on the core, or a system Verilog-based testing. There are areas of design which does not include C-based testing. For that, one size fits all is not the approach. Your UVM, as I mentioned, comes with a lot of overhead, which may not be desired. Similarly, C-based test cases may not be desired. You may need several hours to boot the whole system and program the IPs. Probably that's not needed for certain part of your verification. So you need to analyze your testing infrastructure and approach for each test case categories and find the right combination. It could be somewhere in between. So it could be on the one side of the spectrum. That should be part of your considerations. Another set of technologies is simulation or emulation. One is very fast, but it doesn't give you enough visibility. What happens when your test case fails? Can't do much, and is expensive hardware. The other side is very slow. Before you can do anything meaningful, even that's a very slow process, but it tells you everything, what's going on in the system, and relatively less cost and easily scalable. So you have to pick the right technology for the right problem. Closure is one aspect. You can carry on forever. You have large design space, large RTL lines to prove that they have been triggered. Areas where formal verification can be applied is there, but it may end up that your properties are not closing. Tool is not able to say that all the properties are nicely verified, even running for weeks. So are you happy that certain property was not proven? No counter example was given. That may be okay. You may have a lot of assertions in the design. Do you want all of them to be triggered and say that they are passing? It may not be needed. You have to have protocol checkers in certain part of the design, but is that a brute force you want to apply where all let's say AXI data pass should have AXI protocol checker in the system? It may not necessarily be the case, but so there's a list of considerations that you need to apply. You may need to hook up functional coverage, but not close it to full extent. Do you need to have code coverage closure for all the blocks, or even for the outside the blocks? Do you need to do protocol coverage closure when you have a protocol checker? It may not be needed, but may be needed where you have glue logic because there's a fresh piece of code. You have clock domain crossing. Now, the server-based application example may not have a lot of power domain crossing, but you need to have clock domain crossing nicely proven. But again, what's the criteria? Do you want to put your CDC checks everywhere and make sure that all the test cases pass, or a certain list of test cases? Because when you have a clock domain crossing from one part of the system to another, you don't need to simulate for that test case the rest of the system. Only that data path need to be proven. For that, only a slight certain amount of test cases may be applicable. But again, you need to invest time in analyzing that. Or a brute force approach can be more useful. And power verification, we haven't discussed that. That's another key aspect that you need to make sure power aware simulations pass. A lot of randomness can be applied. For instance, there was a question initially. Do you need to prove that you have sufficient number of runs? Typically, when you have random UVM-driven coverage, you need to have 1,000 test cases to prove that you are happy with that. Do you need that? And do you need even so all the test cases should prove an OSB. So these are some of the criteria that should be part of your closure. And when you say I am done, it may not be that everything is, or maybe or may not be. It depends on the situation. But you should have the right set of test point, right of your coverage closure points. That when you can say that you are comfortably done. FVP, right? So one of the problem is when you want to implement test cases, let's say test case in C, where do you execute those, right? You don't have a system yet. Designers are still busy stitching everything. You need RAM and ROM implemented before system can boot. You need to have interconnect connected nicely so that transaction pass from one end to the other before system boot is reached. So basically, you're talking of a very long initial setup time for your verification activities. Ideally, you would like when your specification is ready, you should be able to, you want to start as soon as possible because a lot of initial hurdles you can pass through relatively easily. But for that, you need your design there, but it's not there. It will take some time to be. So one of the approach here is, are there models of the system which you can utilize and simulate? So fixed virtual platform, so running at speeds, so at the right frequency, compared to the real hardware, FEPs are complete simulation, including processor, peripherals, and memory. This gives you programmer view. Programmer view means you have necessary information to write the code, which gives you a comprehensive view of the and it's a comprehensive model where you can start. So if you have this at your disposal, there's no need to wait, especially for the C-based testing. Right. So essentially, it gives you a software head start for software build-up, but bare metal testing is kind of writing initial software. So in theory, you can start building up your test cases even when you don't have an RTL. But nothing is free. So FVP is generally ahead. They are simple models, transaction-based. They are generally ahead of design and verification cycle. So and therefore, it makes a case for that. Could you use it for test case development? They are very fast. It's not like RTL. So it's basically, I would say, fair to say, zero simulation time. So there's a huge argument to be able to use those for verification. It provides, to some extent, capability to assist in test case debugging. Some of the fundamental debugging tools like Tarmac could be used so you know what's going on at your instruction level. So you can debug the test case. But the cost is there could be limitation of functionalities in FEP where you may not, but it's not a big one. But the main issue can be that FEP is a representation at it's not cycle accurate as RTL. So there may be consequences of potential rework for your test case. You can debug the test case, but you don't have a real hardware. So that part you still need to tackle. There could be bugs in the FEP. So you need. So when you are doing this kind of testing, you may hit into issues which actually are not your prime target. Your prime target is to find out the bugs in the RTL. So could there be potential waste of time? Well, waste is a strong term, but that is not your prime target. You want to use FEP. You don't want to verify FEP. So There is a case for that. Still needs careful consideration. Like this is one area which could give you a head start, which is very useful because when RTL is there and you have your regression suite ready, it's a great place to be in the whole activity. All right, that concludes more or less my talk. Just to recap, so for some hyperscaler SoCs, CSS in this case, reference design compute subsystem, you have a very large verification space and you need to take into account for a lot of functional, but can't ignore the non-functional requirements. It has verification involves very complex features, both in terms of specification and execution. Choice of design plays a significant role in the successful closure of verification. Design and verification need to be talking. Configurability of test bench is a complex subject. So there have been several questions on configurability of subsystems, how to verify. But it's a complex subject. It's very difficult to implement test bench which can cater to different configurations. Often you would like to select few configurations which represent your full configuration space. For instance, if your data width can have values like 32, 64, 128 and higher, do you need all of those? Do you maybe to take one smaller or the last and take one in between? But still, it's a complex subject to build up test bench infrastructure as well as test cases, firmware, everything configurable. Large RTL size and therefore test bench as well is a big problem for simulation speed up. Emulation could provide alternate and simulation are complementary. You need to make the right choices. FEP as an alternative platform can be explored. Yeah, with that, I guess I took a lot of time. Thank you very much.
Any questions?
Yeah. Yes.
If you are verifying an IP, should it be design spec compliant or a subsystem scenario compliant?
Yeah, let's start from the basics, right? So what is the specification of the IP?
Specification might be generic, right? It supports across the systems.
Oh, well, does the product requirement says that your IP needs to work with that subsystem? If so, yes. If not, which typically would be the case because IPs are meant to serve full spectrum of design space, often it would end up at the boundary of protocol. But it may refer to a use case. So to give you an answer in a nutshell, answer is no. It should be complete on its own. It should be a complete representative, fully verified. If there are requirements or may not be strong requirement that it should work with that subsystem, then you need to bring that into verification flow of that subsystem.
If you are testing IP or a subsystem, should the RTL be, will the EDA tool take care of the synthesis or we have to test it whether the RTL is synthesizable or not?
No, so there are separate EDA tools which fully take care of this problem and they should be bring into your design flow, preferably early so that before you hit into those problems in verification, they are taken care of.
Thank you.
Any more questions? Yeah, sorry.
Sir, as you said, FVPs are not cycle accurate. So if we are developing any test cases around FVP models, so again we need to do when the RTL is developed. So isn't it double the effort? And
so that's the point. It may not be double the effort, but it can give you a head start. On a whole picture as a whole, it may give you less effort. So that's the point. It's a transaction based. So there could be test cases that that are coded at cycle at transaction level. That's a memory map testing. You access certain memory locations or memory apertures. You don't need a test case coding level, you don't need cycle accurate behavior, right? And suppose your FEP says, yes, your test case is ready. You can read and write to that location with the right security attributes. So at least what you have done is you can compile your test case. You have infrastructure in place where you can actually simulate the test case, which can be a big point actually when you are starting from scratch. You are getting to the place where you can write C code. You need a lot of bare metal drivers for IPs. Your test bench infrastructure need to be in place. Your software firmware infrastructure need to be in place. That means all of that is reasonably there. It's not verified, but it's there. You can write test cases. So that start has been done already. And when RTL is there, you are simulating. So there is your time saving. What can be the problem is that your test case fails. Naturally, there are bugs in but you have taken a head start, and your test case is when it's failing, you are straight away meeting your objective. So in this example I gave, you have a reduction in effort. Proceed.
Sir, if you are verifying an subsystem or an IP, if there's a 2-cycle latency or something, and that is not necessary in that subsystem, but how do we find out via verification that there's a 2-cycle, we can make a 2-cycle improvement of?
So if it is relevant, it should come up in your performance testing requirements. If your bandwidth is getting killed because of certain data path implementation, your performance benchmark execution should bring it up. Otherwise, functionally it is accurate, performance-wise it's accurate. Is it material?
Okay, thank you.
Sir, when you said FEP has debug capabilities, so how do we proceed? Like it goes to same thing while in AI and ML we store all the best known strategies of debug at one place, and whenever we are doing a simulation and something fails, you go back to that database and find out what is failing. How are debug capabilities in FEP execute?
I don't see the link between debug capabilities and AI and ML. Right. So debug capabilities, what I mean is you can open the code and you can see which transaction was taken, which value in the model, and also your test case you can do some instruction-based debugging, for instance. But I don't see the link between AI because the problem with AI are still the same. You need data to train your model, which may not be that much available for a system. So AI, I don't claim that it is helping in debugging.
FEP.
It does not take data. It takes an objective function. It's also an AI.
No, but FEP debugging. So can you rephrase the question, please?
So when you said we have debug capabilities for FEP, so you said without RTL we can start using our test cases because we can start building our test cases.
Yes.
So without getting the RTL, how we will give debug strategies to the FEP? How will it know before coming?
So you are debugging the model, not the RTL.
Okay.
But that you can debug. For instance, in a memory map test case, you want to write to a certain location. And suppose your model does not give you the right data back, your test is failing, you can debug to basic extent.
Okay, that's anyway manual.
That's a manual process.
Got it.
Okay. Thanks, Alok. I think with this, we'll take like a 10-minute break. So we'll get the part 2 next presenter ready as well. Okay. So refreshments are on the left side. So we'll be back at 11:15.
What's the size of the subsystem?
Take a break. Sure. Good. Somewhere here. It says battery is low, so perfect.
Hello. Is it hearing? Hello, mic check.
Yeah. This is a pointer. Slides. Oh, just turned off. Okay. Let me go forward. And then it also has a pointer. Problem?
The red one first.
This one?
Yeah.
Yeah.
Okay.
Anything else you need?
No, this should be.
How much time you need roughly?
Huh?
How much time you need roughly?
45 to 1 hour.
You people asking questions, okay?
Yeah,
Get
that's
sitting
fine.
here.
Yes, yes. Perfect.
I'm sure some version of it will come out.
That came after this. That announcement came after slides of it.
All of the flows are very similar. And it's fascinating, but it's not bad. I know, but sometimes it's up and often, by the way, the information's wrong. Like I put in something that you said, hey, what's the relationship between light power and quality? Anyway, so it comes back. Light power is a technology. Now you call acquisition. And then you have very confident. So it's like, what's the name? This
Okay, I think we're ready to get started with part 2.
anyway, so I said,
So if you guys can settle down, we will get started.
I know it well.
Okay, we'll get started with part 2. We have Arul Vasan here. He's working at ARM in Bengaluru, and he's been with ARM for like 5 years, and he has a total industry experience of around 13 years. And his primary area of work is in simulation, and he has a bachelor's from PSG College and master's from BITS Pilani. So I'll hand it off to him and get started.
Hi, everyone. Thanks for the introduction. Welcome you all to the session. So, my agenda is so I'll start with a little introduction on the multi-chip
compute systems. So how they look and what are the different multi-chip use cases. And then I'll go a little bit into what are the typical verification scenarios in a multi-chip compute systems and the challenges associated in the multi-chip verification. And then finally, how we address those challenges. So that's the agenda of this session. So let me start with uh, the first part. So what is a multi-chip compute subsystem? So in the previous session, you would have seen Alok explaining, showing you a compute subsystem with all the key blocks. So that is a single chip, that is a single compute subsystem. So when you put and when you combine subsystems, similar subsystems together, it becomes a multi-chip compute subsystem. So it could be a multiple, so your multi-chip system could be multiple chips inside a package, SoC package, or it could be even multiple SoC packages connected together. So both are multi-chip compute subsystem, multi-chip systems. And if the chiplets in the multi-chip system are same, then we can call it as homogeneous. And if the chiplets are different, we can call it as heterogeneous. But one point is, it is for the operating system or the hypervisor, it is a single system. So though physically there are multiple chiplets, there could be multiple packages, but the operating system or hypervisor which is going to run that system, it will see as a single system. It doesn't worry about the physical part of it. So that's multi-chip compute subsystem. So yeah, to connect the chips, you need some protocols, and those protocols should be cache coherent protocols. So ARM NeoVS based subsystems or systems support these protocols, CML SMP, which is very close to C6. It's called coherent mesh layer SMP. SMP means symmetric multiprocessor, and it also supports CXL protocol. So we use these protocols to connect the chips. These are cache coherent protocols, so that all the chips are in the system are cache coherent. So typically we use the CML SMP protocol to connect to the accelerators, to the memory devices, external memory devices, sorry, host to host SMP connections. And we use CXL for connecting to accelerators and memory devices. So we will look more into these things in the coming slides. But just in this slide, I just want to highlight about these two protocols, CML SMP and CXL. So you have seen this diagram in the previous session. So this is a single chip system, and here is the processor block. So NeoVS based systems, okay, supports up to 128 cores. 128 processor blocks can be present, and this is the intercontroller, and this is the cache coherent interconnect, and here the box that is in a red color, right? Here is that interface to connect to a remote chip. So we call this, there is the CXL protocol or the C6 protocol. That interface comes here. So through this interface, we connect to a remote system. That system can be a system similar to like this, or it could be a completely different accelerator system, or it could be an external memory. So those connections will happen through these interfaces and using this C6 and CXL protocols. So let me maybe a typical example, assume that the processor here wants to access. So here, this is your DRAM controller. Your DRAM will be connected here, and assume a system like this. Assume two systems like this, and their CX. This interface is connected to that, and assume that the scenario is the processor here wants to access a DRAM in the remote chip. So that typical, that transaction flow, how it will happen is the processor will send the transaction to the cache coherent interconnect, and it will take this, it will be converted as CXL packets, and it will be transported outside. It will reach the next system. In the next, there will be again CXL protocol. The transaction will enter into this, will reach the interconnect of the remote system, and then it will reach the DRAM memory controller, and it will access the memory. So that will be the typical, a basic DRAM access flow. So the point is, I just want to highlight here that, yeah, the CXL or the C6 is present here, and the CXS is a transport interface, and CXL is like a transaction layer protocol. So transact, and this packet will be converted into CXS, and then it will be going to a file layer, and then it will go to the remote system. Yeah, so these are the typical host-to-host SMP connections. So when we say SMP, it means that we have a system, two systems connected. These are all mostly I'll be talking about homogeneous systems in this session. And the first one is two compute subsystems in a same package, and we usually call this as a socket. There's and this or it's a socket, and it is called as a dual chip system. And the protocol that is used to connect these two systems are CML SMP, and usually the CXL protocol is used to connect to an expansion memory. So this is one example of the SMP multi-chip system, and this one here you see two sockets. Each socket has two die, and this is a quad system. And assume if it is having each system is supporting 64 cores, then it means this whole system is having 256 cores. And the third one here, each package has only one compute subsystem, and here there are 4 such packages. Okay, and this is not actually an SMP, but just we just wanted to highlight here that you can connect to any number of expansion memories. So in this case, in the SMP case, the systems are same. The chip 0, chip 1, 2, 3, all are same, all are homogeneous. And here, this is an example of host to accelerator connection. So this is your compute subsystem, and this is your accelerator, 2 separate dies, and they are connected using the CXL protocol. So this is an example of an heterogeneous system. And yeah, so your accelerator can have caches, and the entire system, these caches will be coherent with the main system. So everyone sees the consistent view of the shared data. Oh, this is just a host to memory. This is your compute subsystem, and you're just connecting an additional memory. Again, the protocol used here is CXL. So the purpose is to add further memory capacity. Okay, so whatever we saw now are typical multi-chip systems. So now I will take you through some of the typical verification scenarios in a multi-chip system. So first is memory map verification. So in an SMP kind of multi-chip system, so assume take an example of quad chip system. So each chip will have the same memory map, and each chip can access any chip's memory map. For example, chip 0 can access all of chip 1 region, chip 0 can access all of chip 2 region, chip 0 can access all of chip 3 regions, same vice versa, chip 1 can access chip 0, so everyone can access everything. And that is one, so that forms a major part of the multi-chip verification. So assume that your total memory space is 16 TB. Then typically we divide that 16 TB into among the 4 chips, each 4 TB. And yeah, so we make sure that each chip is able to access each other chips, region, memory, the IP, everything except. So that's memory map access. Next is typical data flow that can happen between chips. So usually the traffic that flows between the chips are accessing the remote memory. So chip 0 accessing a memory sitting in chip 1 or chip 2 or chip 3, same way, vice versa, chip 3 accessing a memory sitting in another chip. So that is the memory traffic to the remote memory. And then your cache coherent traffic can go between these chips. You can do a coherent read and write to a remote chip, and you can do cache maintenance operations to a remote chip, and then you can snoop the cores in the remote chip. So these are some cache coherent traffics can go between these chips. And you can even so in the case of memory management unit, even you will see a translation table, page table invalidation requests, going between the chips. And again, interrupts, you can interrupt messages can just go between these chips. So these two diagrams, the difference is the connectivity, how they are connected. So in the second diagram, the data path can be, if chip 0 wants to access chip 2, it will go to chip 1 and then it will go to chip 2. So this is ARM allows this, but yeah, this is most preferred. Latency will be very less here. In this case, here chip 0 can talk directly to the chip 2 or chip 3, any chip, but in this case it should take some more hops. Okay, so interrupt communication. So in a multi-chip system, right? So the interrupt can be from any source, the interrupt can be generated from any component in any chip.
Yeah, just one question.
Yeah.
So when the Snoop requests go from one chip to another chip, what about the delays? I guess the delays are so huge that by the time the Snoop request goes to another chip, the first chip might have updated the cache line. So in that way, the next chip will not get the latest data. So what is the implication of these delays across the chip?
No, so the CMN here, right? So this is the point of coherency. So this guy will take care that if there is an outstanding Snoop, okay, so already there is a Snoop request which is outstanding, then it will make sure that any other guy who is trying to access that will be delayed. Okay, so it won't be updated. So that will be handled by the cache coherent interconnect, which is the point of coherency. Okay.
Okay, so till I get the acknowledge from the other chip, I shouldn't update this cache line here.
Yes, correct.
Okay.
Yeah.
Thank you.
So the protocol has those definitions, or the rules when to update the cache line, or when, so it will not be corrupted. The data will not be corrupted. Okay, so coming back to interrupts, so interrupt can be generated by any device. It could be your PCI device could be generating the interrupt, or your watchdog timer could be generating the interrupt, or counters could be generating the interrupt. Anybody can, tens of thousands of interrupts can be generated from a system like this. And the mantra here is, these interrupts can be serviced by any core in the multi-chip system. Okay, so let's assume an example. So there are two chips, chip 0 and chip 1. And, the source of the interrupt is from chip 1. So what happens is but that interrupt needs to be serviced by a core in chip 0. So what will happen is, the interrupt is generated. There will be a local interrupt controller in each chip, and so the interrupt will be routed to the local interrupt controller. Local interrupt controller will have the details, who should service that interrupt, which core should service that interrupt, whether it is a core sitting in the local chip or it's a core sitting in the remote chip. So based on that information, if it finds that if it finds that the interrupt should be serviced by an interrupt in core in another chip, it will route that interrupt via the CMN and all that CXS interface. It will route that interrupt message to the remote chip interrupt controller. Then the remote chip interrupt controller will schedule that interrupt to the respective core. So this is cross-chip interrupt communication. So all these interrupt controllers very sync. Yeah. Any question? Okay. Yeah. Okay. Yeah. So all the interrupt controllers will be in sync. They will have the same data. So yeah. So there won't, if the information, the interrupt vector table, all the information in this gig D and this gig will all be the same. So everyone knows which interrupt should be serviced by which core. So that's how it is managed. So this is doing this cross-chip interrupt verification is also one of the verification item in a multi-chip verification. Next is timer synchronization. So each chip will have, if you've seen in the previous session, there was a peripheral block and that had a lot of timers, counters. There will be generic timers and counters. So each chip will have generic timers and counters, and it is very essential that it is a single system for the operating system or the hypervisor, right? So the timestamp should be same for each chip. So it is very essential. It cannot be a counter in chip 0 and a counter in chip 1 cannot have different values. Okay, then your software can corrupt or your application can corrupt. It will become, so it is very essential that all the counters in the chip are counting the same or running same. So but it is not possible, right? So somewhere there will be a drift. One counter will be fast, another counter will be slow. So it is essential to synchronize those counters periodically. So that that's timer synchronization, and multi-chip verification should take care of that. Should make should create different scenarios where the timers will diverge and they will sync. Usually what happens is one of the chips in the multi-chip compute system will be will be assigned as master or primary chip, and the other chips will be synchronized to that primary chip. So that's how it works. Next is debug and trace. So yeah, we should we should be able to debug the multi-chip systems. We should know what is happening. We should be able to collect the trace data, and we should be able to debug the multi-chip system. So typically what happens is the DAP or the JTAG interfaces are daisy chained, and your external debugger will be connected here, and your external debugger will be able to read the debug data, everything. And yeah, so this also each chip can send a trigger to another chip or an event to another chip, and each chip can you can send a trace data of one chip to another chip, or you can send it to a trace data of one chip to a remote chip memory. So these are all the typical verification scenarios around the multi-chip debug and trace. So this also verified. So other verification scenarios, NUMA, non-uniform memory access. So how do you group so we are talking about cores in hundreds count. So how do we group those application cores? So it's a very very well known terminology NUMA. So what we configure a group of application stores to share the memory. This is for faster data access. So this itself opens up a lot of space, verification space. So you can combine your application cores in any fashion you want, and you can combine, especially in a multi-chip system, you can combine cores across chips. So this is one area of verification. And power and reset. Your one of the chiplets in the system can be power, can go into low power, or it could become faulty. We have to so the different combinations are possible. So all those power up and power down of chiplets is a verification scenario. And mid simulation, reset and boot. Okay. And last, security. Uh, you know, okay. So when a transaction crosses the chip boundary, right? So the security and the privilege attributes do not change. Okay, so if you're trying to do if chip 0 is trying to do a secure access to chip 1 DRAM, that secure attribute should not change. It should not, a secure access should not become a non-secure access. So that security needs to be checked. So when in all cases of data flow or snoop or whatever, the security part should be it should not change. So that's also part of multi-chip verification. Not able to change. Yeah. Okay. Yeah, the next one. Okay. 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 But this echo. Okay. Still. I think I have to mute this. The laptop is.
It's good now, Rayappa. It's good. The
Okay.
slide view is correct now.
Okay, so that's all about the typical verification scenarios. So next I will try to, I'll move into the verification challenges. So the system size. So even in, see, the single chip system itself is very huge. Each core can have up to 128 cores, and interfaces, there could be 100 plus interfaces. So it is impossible, to connect VIPs at all the interfaces. I'm sorry. And so we are talking about memory map of TBs. So it can support up to 256 TBs. So and your DDR can be really close to 256 TB size. So it is really not possible to connect a memory model of 256 TB size and simulate. Right. So and when you put a quad system or dual system like this with 256 cores and thousands of interfaces, your simulator is literally going to cry. So it will be very, very slow, or it may not even, if you don't take care of it properly, we may not even able to simulate a multi-chip system in the simulator. So system size is a very big challenge. So the next is, you have to, there are different multi-chip configurations are possible. So a product can support dual chip configuration, a quad chip configuration, or it can connect to a different accelerators and external memory external memory devices. So a lot of combinations are possible here. And it's very essential that our test bench and test case development are very robust, and we should not end up writing separate test cases for each of these configurations. So then it will become a huge problem, and time to market will become a problem. And again, like in the previous session, so the scope is very large. A lot of IPs are involved, and each of these IPs comes with thousands of parameters. So IP configuration is again critical here, and again the NUMA configurations. So a lot of configuration, a lot of combinations are possible here. So the verification scope can become very large. So we should take a proper decision where to stop and which configurations to test. Coverage collection, again, so it's a big system. If you want try to collect code coverage for everything, every block, and do an extensive functional and statistical coverage, then you are going to end up with a huge number of huge data. And it can, again, the simulation can become very slow. So yeah, coverage collection will also be difficult in a multi-chip system. And debug tools, yeah, so waveform alone may not be enough. We should have some better debug tools. Just waveform, it's difficult to dump all the signals in the waveform also of a big system. It will be slow. You need more memory. So there are challenges here also. And checker or scoreboard, if you want to implement any test bench components, it can become complex because each chip has hundreds of interfaces, and when you have dual or quad systems, yeah, so you have more interfaces to tap, monitor, and then your checker or scoreboard will have huge data. So it will be your implementation can become complex. So we need to be very careful in implementing test bench components. And again, runtime can be very huge. So it's a multi-chip system, so you have to boot all the systems. So your boot itself in simulation can take a day, and then your you are running the scenario can take another 2 or 3 days, depending upon the the scenario that you want to test. So your runtime is going to be very long. So we need to come up with a better idea to to address this runtime issues. And yeah, when large number of, and yeah, okay, we'll cover this, how do we address these challenges, we'll cover it later. But yeah, runtime can become a big issue, and you need a huge HPC, high performance compute requirements. Like I said, it's a big system. You need huge memory. You need longer runtime. So you need that high performance compute infrastructure to run your simulations, for collecting the coverage data, everything. Okay, so maybe next topic is how do we address these challenges? System size. So like I said, multiple cores. It's really difficult to simulate, 30, even 32 cores is difficult. And so assume 64 or 128 cores in a chip, it's going to be very difficult. So we need to, we cannot, so we need to have some smaller systems with less number of cores represent, and, we can do a full verification of that. You can use that for your test case development. So typically what we can do is, assume a 32 core system, you can just enable few cores and tie off other cores. Or you can replace cores with some lightweight models so that, your simulation can, there will be some improvement in the simulation time. And multiple interfaces, there will be multiple interfaces to connect to PCI devices or your accelerators, everything. So don't try to connect, you should have a controlled instantiation of a control on the instantiation of the VIP and test bench components. So you can develop multiple test bench, as per the need of the test stimulus. Memory, we really cannot enable 256 TB memory. But we can go for sparse memory models, or we can use some lightweight memory model footprints. Multiple configurations. So like I mentioned before, we can have some smaller system. So use smaller representative system for all your test development. For example, have an 8-core system instead of directly targeting an 128 core system. You develop your test cases, flow flush everything on a smaller system, and run your test case and use 128 core system only for regression. So that way, you will have lesser problems, because debugging a 128 core system is difficult. And but I mean, especially when we wanted to fix the test bench issues and test issues, a smaller system is best. So, and scalable and reusable test bench. Always, make sure that the test bench and test cases that you create will work for multiple configurations. That means it should support dual chip systems, quad chip systems, or any accelerators, all those things. So go for parameterized implementation of the test bench and test cases, and if possible, reuse test cases from other levels of verification. Like, there could be some test cases written at single chip verification level, so you can reuse that test case in your multi-chip level. So, but that needs an alignment of the methodology used in these levels of verification. So yeah, it helps in the turnaround time of test development. Yeah, so verification scope challenges. Like we have different IPs with a lot of parameters and NUMA configurations. So here we need to. This is multi-chip, so we that itself will we need to identify the multi-chip related parameters and focus on that. Anything non-multi-chip should not be verified in multi-chip scope. It should be allowed to be verified in IP level or single chip level, and give focus only for multi-chip scenarios. That way you reduce the scope. If you try to target everything in multi-chip verification scope, then it will be very difficult to close the verification. So smart dumping of waveform data, you cannot really dump, it will be too much. So dump your waveform only for a selected window in the simulation. You can have some automation here based on the timestamp where you are seeing a error or something. You can just rerun and dump waveform only around the timestamp. And you can come up, develop some smart transaction loggers, which you can connect at different interfaces in the system and see how the transaction is flowing through in the system. So these all will help in the debugging a multi-chip compute subsystem. And in the coverage, so again here, don't worry we should should not worry too much about single chip or IP level coverage. The focus should be on multi-chip. So even for code coverage, you can enable the only the blocks and the interfaces that impacts the multi-chip. For example, in the first in this diagram, there was the CXL interface. So you can just look at the coverage of that. You don't need to really worry about coverage of other interfaces in multi-chip verification scope. So yeah, so it is collective. So we need to rely on for a collective 100% coverage, right? We need to rely on unit level and single chip level verification. So targeting everything in my multi-chip environment is difficult.
A few questions here.
Yeah.
So when you talked about the runtimes in multi-chip verification, so did you try save restore option, and do you see any limitations even with that option?
Yeah, so save and restore, we tried it, it worked, but in a UVM environment, it is little difficult because it is, if your test bench is UVM, as some UVM components, it's difficult to save the state of that UVM or the classes, all those things. But if it is a C-based test environment, yeah, save and restore worked. We are no limitation. So we are able to save the state. Next time we can load that and you can proceed.
Okay.
Yeah.
And one more question. Do you use same boot code for the single chip verification and multi-chip verification, or you use separate boot codes? Why? Because in case of multi-chip verification, there should be synchronization points between the chips.
Yes.
So what approach you follow? You use the same code or different codes?
Yeah, so we need, like you mentioned, synchronization is required. So the boot is, but still the boot step for each chip is the same in the system. So that is same. We take it from the single chip environment, and then on top of that, we add the synchronization logics.
Okay, apart from synchronization points, you don't see any difference between the boot codes for single chip and multi-chip, correct?
Yeah.
Okay, and just a couple of more questions. When all these chips can be reset independently, or is there any constraint that they should be come out of reset together?
No, they can be reset independently.
Independently.
Yeah.
Okay.
So then, it will be synchronized during the boot. One of the chip in the multi-chip system, right, will be designated as primary chip, and that primary chip will, can monitor the other chips whether they're booted or not. All those things. That's possible.
Okay, and just one last question. Since you have connected the JTAG in a daisy chain fashion for all the 4 chips, so all those 4, those are dice in a package, or those are separate packages, all 4?
No, it can be anything.
So if they are separate packages, I'm not understanding the need to connect the JTAG in daisy chain fashion, because it is mainly used to verify the manufacturing defects. Yes. So in that way, all 4 are independent. So
agree with you. So yeah, it does. When it is different packages, yeah, it may not be required to daisy chain.
Okay. Just I want to understand the need for that daisy chain connection across the chips.
It depends upon the how the multi-chip system, whether as you mentioned, whether it is same package or it's a different package.
Okay, thank you.
Yeah. So coming back to test runtime, wherever possible, you can adopt some fast system boot methods. You can skip some steps in the boot, and or you can come up with some other methodology and find some fast boot methodologies. You really don't need to, sometimes you really don't need to boot everything. Okay, so depending upon the test scenario, you can skip some steps so that your boot is faster and your overall simulation time is faster. If you try to do a full boot every time, most of the time goes in the system boot itself. So you can find some optimization here, and the verification engineer also should be aware of the runtime issues. Really not advised to create all scenarios addressed in one test case. It's better to divide the test scenarios into multiple test cases. So a runtime aware implementation is very much essential here. HPC, so yeah, so again here adopt fast boot methodologies, and you can break down your bigger test into smaller tests, so that you can keep your overall regression runtime within 24 hours or 1 or 2 days. So this will help. Yeah. So that's all I had. Any questions?
One question I have.
Yeah.
On this independent reset that you mentioned for the different chiplets, right? I mean, let's say one transaction is starting from chip to chip, and in between somebody is triggering reset for the receiver. How you gracefully exit from this?
Can I take your question as like in a dual chip case?
Sure.
So you're saying that if there is an outstanding transaction, how you will reset another chip?
Yeah, yeah.
Yeah, so so there is the CXL and these protocols, right? CXL and CMLS. If there is an outstanding transaction, then this power up and power down has a sequence. So when you have an outstanding transaction, it is not possible to switch off a system.
But then
okay, if you do some hard reset or something, you are going to lose the transactions. The system behavior will not be we can't predict.
Okay.
Yeah. Any other questions? Anything?
Okay, if not, we'll move to the presenter. Thank you, Arul Vasan. Yeah. Hello. So let me introduce you, Vikas Chandra, right? He's been working at ARM for 8+ years, and overall industry experience of 20 years. And he has a ton of experience in PCIe verification. And currently, I think he's working on PCIe and CXL verification. He has a bachelor's and he has a PG specialization in VLSI from CDAC Hyderabad. So I'll let Vikas take over.
Hello, everyone. My scope of the presentation is emulation-based system-level verification. So why we choose system-level verification before the subsystem goes into SoC, as well as why we choose emulation as the platform for system-level verification. So mostly I'll be dwelling and the challenges in emulation-based system-level verification I'll be touching upon. So in ARM, for an IP or a subsystem, there are different levels of verification we do. So IP starts with a unit level verification, where within an IP, a unit, like, you take a coherent interconnect, there will be a request node, a unit. I'm giving an example of a unit, a request node where the DSU is connected or a core is connected. That is called as a unit, and that unit will have its own verification environment, its own verification plan. And when it comes to the whole interconnect as an IP, there is a top level environment. So interconnect will be having a test bench where, or a core will be having a test bench where it will be connected with different VFMs and VIPs to simulate scenarios to verify that IP at top level. So there's a unit level verification, there's a top level verification. Post that, we do a system level verification to classify any IP's quality or for an IP quality milestone. There is a sign-off criteria for system level also. What changes in system level? We connect ARM IPs together, like an interconnect and a core and an interrupt controller, which is the subsystem which you are seeing. So we, at IP level verification in system context, what we do is we connect these ARM IPs together and try to verify that IP in system context. So IP verification at unit top and the system little differs in terms of verification scope. So in system level, we try to verify the interoperability of ARM IP with each other, as well as stress ARM IP in system context. When we say in system context, suppose my scope of verification is an interconnect IP, or my scope of verification is a core, the verification plan will slightly differ, where we'll try to stress that interconnect in a system level, or stress a core in a system level, or an interrupt controller in a system level. So it will be more focused on IP, but it's in system level verification. Another aspect of system level verification is the stress. So we want to stress the IP with running more faster or more cycles we want to run in that IP in system. And we try to find if IP breaks when it runs for billions and billions of cycles. For that, simulation is not an option. You have to choose emulation or FPGA, different platforms, to synthesize those designs into emulation and FPGA and run billions and billions of cycles. You need to have tools of verification which is designed to do stress verification, which is who are involved in processor verification will understand. There's something called random instruction sequence tools, which is very prevalent in CPU verification world. So we use random instruction verification sequence verification tools, which dumps out random instruction sequences. Along with that, we use other standard peripherals or third-party peripherals attached to our system to simulate on the I/O side or on the peripheral side. So along with random instruction sequence being executed by core, we give all the other stimulus which is needed for an SoC. And that's where we stress the IP in system context. Okay, so there are two major things we will keep in mind is interoperability as well as stressing the IP. Now, how do you feedback? There were a lot of questions on AI, ML, and how do you feedback and improve on your whether stress is enough or not? What's your qualification criteria? So in system level verification, we have two qualification criteria. One is cycles run on that particular system or that particular configuration. Other one is statistical coverage. It's not a functional coverage, it's a statistical coverage. So in your IPs, there will be different signals or different events which can tell you how many times a eviction happened, how many times a buffer was full, how many times a buffer was empty, how many times translation happened. So these events, how many times it was hit, will give you a sense of stress verification happening for that particular IP. So each IP, we decide on those events. It can be combination of micro architectural events and as well as something we have baked into our IP, which is PMU, Performance Monitoring Unit. And that unit will have some events to trigger to take the count of the performance. And those events we use to give a statistical coverage dump for particular IP. So for an interconnect, how many times, SLC, the cache miss or, hit was done on a core, different L1, L2 hits. So, and also we try to see the configuration coverage. So one is the statistical coverage, other is the configuration coverage. There were a lot of questions on how we are sure that, all the combinations and everything is, taken care. And in case of IP verification at system level, why I'm talking about IP? Because it gives you a background when we come to system level, subsystem verification. So for IP, what we do, we have a configuration coverage. Configuration coverage in the sense, all the different IP parameters like, cache sizes or SLC, no SLC, or different internal IP parameter configurations are measured across emulation, and those things are analyzed whether all combinations were hit or not. Definitely, there is a constraint built into it in terms of valid and invalid combinations. So what happens is, okay, coming to subsystem. So it just the scope and the boundary of the DUT changes. When it's IP, we connect with other IPs. IP is in focus. But here we are talking about subsystem. Our previous presenters covered in terms of what we do at single chip, multi-chip. But this we are talking, I can relate with IP verification as top level verification. So they did single chip top level verification, then multi-chip top level verification, and then in this we are doing on emulation, we are doing a system level verification for a subsystem, correct? So we need to stitch it with other components in the design. So a subsystem is delivered to us. In case of IP, it is different, where an IP is delivered to us, we get all other IPs, we make a platform, and then connect other peripherals and go about IP verification system level. But when subsystem comes, subsystem is the DUT, where we connect other components of test bench to it, and then emulate it into an emulator or an FPGA. So we stitch the test bench around the subsystem, and then we use RISC tools, which is the in-house tools, to generate stimulus, which we will use in turn to validate this DUT, which is subsystem in this case. And then this emulation-based run and debug. A lot of things, emulation, since it is billions and billions of cycle, the debug part is a bit challenging in terms of, where is the exact failure? How do you corner them in billions and billions cycle? You can't dump everything. So you take use of log files or tarmac. Tarmac is the dump of CPU execution. So whoever has used or participated in CPU verification will be familiar with tarmac. So you have a disassembly of your software, which is loaded into the memory, CPU executes, and that disassembly you compare with tarmac, and you try to corner the window of failure and try to see whether live lock has happened or it's a hang, and then you dump waveform around 100 million cycles here and there, and that's how you try to deal with such a bigger window and cornering. So in this, there will be monitors, there will be other log files along with tarmac, which will help you in doing that. So run and debug, just wanted to give you that perspective on emulator. When you go to FPGA, the visibility, though FPGA is not scope of this presentation, but FPGA, when you do, you can do the same subsystem verification, use the same RISC tool in FPGA platform, but their visibility is less. But with a lot of development in FPGA debugging, the visibility in terms of debugging aid, it is improving. So we have in system level, okay. Yeah.
Synthesizable.
Yes.
So, but what portion of the test bench is being synthesizable? Is it the constraints or randomization? How is it that being taken?
It's fully synthesizable in terms of all the components. So I'll give an example. The subsystems which you saw in our previous presentation. So you will see there are IO macros where something needs to be connected, correct? So traffic generator or things like that. Or if it is a third-party IP like PCI needs to get connected. So for system level, what we do is we have our own version of VIPs, which are synthesizable VIPs, are synthesizable traffic generators. So the whole DUT plus test bench gets into emulator. It's 100% synthesizable. So when we talk about synthesizability, it's the environment which is fully synthesizable. Test bench plus the design.
So my question is how constraints or any which we write as part of our TB, those are synthesizable as well.
Everything is synthesizable. Constraints, when you say, you're talking about, so this is C-based processor-driven verification. Okay. So it's not UVM. So I should have said that. It's C-based. So we are coming in system level. We want to come as close as the real world payloads and real world scenario. So that's why when I come to next slide, we have two bare metal testing and OS testing. Bare metal is also very close to when we go to the OS world, but this is bare metal where we use these RISC tools to focus on different areas of verification. And if you see here, different RISC tools focus on different areas of a system. So there is a bare metal tools. Some will focus on memory and system cache testing. Some will focus on IP system level scenarios where IO side traffic generator and the CPU is driving some traffic and producer consumer kind of scenario. So those kind of things. So it's more of taken inspiration from real world payload and scenarios, so and done in a real world kind of thing where your test is loaded into memory, CPU picks it up and executes it. But at the same time, while CPU is executing that, you will have other components in the system which is irritating the system. Or, for example, on IO side, a PCI is connected. You might have a producer-consumer scenario. So one of the CPU is participating in producer-consumer, where CPU is producing, PCI is consuming, or PCI is producing, CPU is consuming, while other CPU is just doing loads. It can irritate. So it's how you use these tools. So tools will have its knobs to create those scenarios. So, and it will give that liberty that the macros and functions will be available. On top of that, you can write your directed macros also. If you know an accelerator, how it's going to behave, you can write your own code. But you have to load it to the memory, it boots, it picks from there and executes it. And that's why, when you're talking about a UVM environment or those things, so we have very, very less, there's almost negligible UVM components there. It's not UVM based environment. It's more close to the real environment. Some places we have used as a component a real IP, like in PCI Express. So what we do is when we go to emulation, why I'm picking a PCI example is because the root complex is an IP in our case, and endpoint is an emulator transactor. So emulator, all different emulator platforms comes up with this transactor solution, where they have a mix of there's something in the box and there's something through DPI calls on the software side, and that's called transactor. So we use transactors also, which each emulator platform gives. PCI standard transactors like PCI, USB, MIPI, Flash, to take few names.
So the writing the test benches which are synthesizable is challenge here, right?
Yes, that's the challenge, and so that's a good question, because we have a centralized VIP team like AMBA protocol VIP team, which makes these VIPs, which is used across ARM, but we can't use those VIPs because we have to use in emulation and FPGA. So we write our own AXI traffic generators, and so this is challenging because we want to emulate the system before it actually goes to partner and they create SoC out of it as much as possible. So when we discuss with our partners and share our challenges in emulation and all, they share the similar thing. Only thing, the scope of duty changes. We do at compute subsystem. They do the same emulation at SoC level. So so two aspects of testing. One is bare metal and one is OS-based testing. OS-based testing is Linux we generally use, and a little bit of Android also on the mobile side of things. But this Linux-based testing has its own version. So it's derived from the main kernel version of standard Linux, but customized for verification. So it's a little lighter version of Linux. On top of that, we can run our real-world drivers and real-world standard drivers and real-world payloads. So with these two approaches, bare metal testing and OS-based testing, we kind of find issues around IP or a subsystem breaks in system scenario when it is run billions and billions of cycle, and if any interoperability issue is there among ARM IPs or with an third-party standard IPs. A slide on RISC tools, because that's the major thing which we use as a stimulus generator. So we have different RISC tools and at different levels in ARM. So an IP level, which is unit and top, also they have a RISC tool, mostly for the core IP verification, the CPUs. They have their own RISC tools at unit and top, but system level team has their own, because we have to give the flavor of system level, and we focus on system level scenarios as well as core driven scenarios. So, and it supports across platform. It supports on emulation, it supports on FPGA, and even on silicon. We are getting this partner silicons back to us, and we run RISC on that. Whether RISC finds a post-silicon issues or not. So we run on our RISC tools on all different platforms: emulator, FPGA, silicon. It's scalable. This is a little stale data. 128 core subsystem, which we were talking about, was also brought up successfully, and we used our RISC tool to validate that. It's completely relies on this live lock, hang, and this kind of verification. There's no standard scoreboard or checker or those kind of things. Though we have some monitors and some indicators, but it is predominantly on a multi-pass, multi-consistency. So two core execute similar set of instructions, and we compare memory, whatever the output memory and register contents are there, and we compare whether it's matching or not. If there is a miscompare, we go and debug using tarmac and waveform. And we have this other tool like Pinaka. We have these, these checks also built in, the directed scenarios and the check built in the test. It's a self-checking test. So those tests are also available, but all the random sequences rely on multipass consistency. Yes, each tool has its objective, and it dumps the instruction sets accordingly. And some works on memory translation, some work on memory stressing, some work on multiprocessor kind of scenarios. And since we use a coherent interconnect, and there are a lot of interconnect focused testing also, because our point of coherency goes to SLC. This is something I touched upon. It's like more of a statistical coverage where we work with designers, IP designers, and subsystem level designers who are integrators to come up with a list of these events, which can give a statistical view of how much we have stressed using those tools. It can be event full or a queue full or a buffer full or empty, number of evictions, at different levels, or any other event which can give you a sense of stress or IP is stressed or not. And those are the event coverages we collect. So at system level, we have three kinds of coverage. One is these events coverage, which is statistical coverage, the config coverage, which we talked about, different L1, L2, and other parameters of an IP, sizes of L1, L2, size of SLC, all those combinations are config coverage, which we are talking about, which makes sense for system level. So system level configurations and the combination of them, whether you have run a particular size of L1 and L2 with zero SLC or not, those things you'll come to know only when you dump these config coverages and look at and analyze that. Along with that, we have a software coverage concept where we say, okay, a RISC tool can produce X number of different scenarios, whether you are running all of them or not on your system. So that is software coverage. So software coverage is also viewed, and in hardware coverage, you have event and config coverage. With all of these, we feedback to the RISC tool if something we are not generating, either it can be supported. So mostly our target of any bug escape or coverage review is to improve the tool around that area rather than just reproducing and writing a directed case, because it is 100% fully random driven, with some bit of flavor of directed testing where we can't do random. So qualification of coming to system level is you have done sufficient, or your unit level and top level targets are met. In subsystem case also, at single chip level, you have targets met, and then of a particular milestone, and then it comes to, or multi-chip targets are met, then it comes to system level. So we are not supposed to, find, though in the process, if we find, then feedback is given to the previous verification team. But we are supposed to, focus on system level scenarios, use case scenarios, third party compliance test, compliance in the sense functional. This is mostly functional verification. So you are verifying with standard third party or not. Like in case of CXL and PCIe, we used industry standard third party IPs and verify those scenarios. Just to give you a very high level, what we do in so it spans across single chip to multi chip, like your boot. So we have seen in past, if we do a bare metal tool boot, which is kind of very representative, or it's bare metal, but there's a thin OS or kernel in it. So a RISC boot gives us a lot of confidence that Linux will boot. So if and one of the tool like Aegis boots, then we have a lot of confidence that Linux is going to boot. And this is like a precursor to the Linux boot. So RISC boot on a full config is a big tick item that system-wise it is ready for at least the basic things, and everything is working. We have our primary focus is coherency, atomics, ordering. So I don't know how many of you are familiar, but there's a distributed virtual messages. So DVM across chip, within the chip, different interrupts across the chip, along with whatever stress you're doing using CPUs. Third-party IPs like CXL, and next slide I'll just cover in terms of our challenges of size and how do we deal in the emulation. But yeah, we have in-house traffic generators replacing cores also. If you want to have a mix of real cores and some synthesizable traffic generators replacing core, so those things also is present. There are a lot of debug aids in the environment which is synthesizable, like AXI monitors, coverage dumps, transaction monitors, which will help you as a debug aid, because in emulation it becomes challenging when you come to debug. All the different areas like RAS testing, when you do in system level, you need to see suppose for example there's a poison, and at memory level there's a poison generated, how it is propagated to interconnect into CPU, how it is reported and addressed. So that kind of system level RAS, double bit error, single bit error, different IPs, how it is dealt with, all those things are verified in RAS. We do clock ratio changes, verification. So run RISC while on the fly you do clock ratio changes between core and interconnect and memory. So those scenarios. On the OS side, we try to run as much as possible the industry standard tests, which is on top. These are application tests built on top of Linux, and we run them on our system and see if there is a break. Or we have our own test written on top of Linux, which is very dedicated test. And that also we use in the SVOS kind of testing, so which is system level OS-based verification. So yeah, so we try to emulate as much as possible close to the real world way of working, and a lot of use case scenarios coming from partner helps us to design this and gives feedback to these RISC tools. So on emulation, again, it's a challenge faced by everyone, not by us. You have limited, emulation platform. When you're talking about emulation, it's a costly resource. It's a shared resource in a company. And when you talk about emulating large designs, you have this challenge of 128 core 6x6 design, or if you're quad chip we are talking about, or 9x12 mesh. So these are very bulky designs, and how do you verify them? You can't run the same amount of cycle on a full config for a certain period of time, which you can run on a small config. So you have to verify. So we do this split and verify approach, where your non-PCI test cases run on a non-PCI build. So you have an emulation build without PCI, you have an emulation build with single core, you have an emulation. So different configs are there, small, mid, large, where the verification space, different verification space is covered. So it is more of a balance between config size and verification space, and some of the configs you target something and other you target something else. So with this we see whether config versus footprint, how we are trade-off is managed. That is one. Other one is you try to use standard parameters where you can reduce the buffer sizes and make the design smaller, but topology wise it remains the same. If it is an 8-core design, it is 8-core design. If it is a 6x6 mesh, it is a 6x6 mesh. But what you do in internal buffers and trackers, you reduce it. That gives you a little bit of size advantage, and that gives you another help in terms of stress also. Like you can stress the design more because you have a smaller buffer and depths are less, so you can fool the design very easily. So different topologies splitting into different configs using internal parameters. Also, we can use design mutations to reduce the size. If you of a particular subsystem, your use case, so instruction IPs are designed with full, keeping in mind it can go into different subsystems or SoC. But for a particular use case subsystem, if you don't need certain set of instructions, you have design mutation to switch them off. That saves some of the logic. So you can use those design mutations to verify. You can stub out design components. I said, suppose it's a single chip design, but IP of interconnect has a CCG block, which in previous presentation Arul was showing to connect to different chip and all. And CCG, if it is a bulkier portion, you can stub out CCG. You can just say that I don't need CCG for this single chip configuration, which is my use case. So you modify IP or you remove components in a system which helps you in verifying targeted system. You can enable disable tarmac because at subsystem level you don't expect IP level bugs. So what you do is, okay, tarmac is not needed. Tarmac adds to the design. So you can enable disable tarmac, which a lot of our partner uses as a technique because they want to come to us for IP level issues if they find any. So they don't need tarmac. So in their regression, there's just disable tarmac. Then we have a mix of synthesizable traffic generator and the real IPs. Suppose it's a 128 core, but still you can have 8 core of real IPs and remaining replaced with synthesizable traffic generators. With this 8 core, you can still boot your Linux or boot your RISC tools and then use the others as irritators. So we can use hardware irritators, we can use software irritators. Software irritator is a core doing some certain set of operations in loop. And a hardware irritator is something, for example, you have, there's a P channel, Q channel, correct? So you are requesting for a power down or a clock gating. So you continuously keep requesting. So there's a hardware component which continuously sends a PREC or QREC, and system is busy. And then that if any bug is around, that you can find out. So mix of software and hardware irritators gives you that stress, as well as this RISC tool running on top of it. So yeah, so I think this is what currently we do, but there are other things also which is in market as a technique, like the co-simulation environment where something is in the box, something is out of the box, and then you use them. The course models can be integrated to emulator, where CPUs are in model if your IP verification is interconnect. So those approaches are also there, and that way. And just touching upon the the aspect of data learning and artificial intelligence. So we did a lot of experiments on understanding this RISC tool, how it saturates the design, how much you have to run, and the cycle versus bug hit, correct? In which area you have hit the bug, how many cycles you have run. So the correlation of coverage, bug, and the cycle was done, and see, okay, how much we can run, how much we can't run. So that's something which is in progress, and we are very serious about taking that as a feedback to our RISC tool. Okay, and different cons need not be run with out of 10 cons, if you run 5, you can hit the same saturation. So if you run for a certain number of cycles, so that correlation is there. But as I said, you need to have enough data to say that that model works. I think, yeah, that's the end of my presentation. But anything related to subsystem or system level verification or verification in general in ARM, I can take up questions on that.
Power estimation analysis on the emulator platform?
For subsystem functional verification project, which is the scope of this, no. But when once in a while, what we do is we take this system to the full test chip. We do all those power estimations.
But my question is, can we do power estimation analysis on the emulator platform?
Yes, we can do. But there are a lot of emulation techniques which is coming now, which will give you a power. But FPGA flows are also there, emulation flows are also there.
But you can share some light. So on the fixed emulation platform, that would be manufactured on a specific, let's say 28 nanometer. We are targeting a 7 nanometer. How is that emulated?
So that's what. So when we talk about subsystem, we don't know the technology node where it is going, correct? So it's very difficult. When it is a product which you are talking about, the full SoC, their power estimation makes a lot of sense because you know what tech nodes you are working on and the IP supporting those tech nodes and what is the power number we are talking about. So if I am talking about a silicon project or a test chip project, there are different flows for power estimation and then validation of those power estimation. Here in functional verification subsystems, we talk about power functional verification, which is like different power states are happening properly or not, and in and out of those power states. How one chip is, if it is a multi-chip system, how one chip is powering off then the other chip, what is the sequence followed, what is the power architecture or power state coverage per se. Like for example, our interconnect has this full access mode, half access mode, and all those things and memory retention mode and all. What are the combinations with that, whether flush is happening, the cache flush is happening automatically. So mostly on the functional side. But when it comes to estimation and all, it's different flow. And I'm not the subject matter expert on the estimation side, but when we go to test chip or any other product, or we are co-designing with a partner, we go into these estimation techniques, which are emulation based also, FPGA based also.
So if I understand it correctly, we can do that on the emulation platform.
Yes, we can do that. Yeah, I'm telling from the current discussions in one of the silicon program where I'm involved, where a lot of emulation vendors are presenting the emulation techniques to do power estimation. So bringing the waveform run on emulation and using those tools to come up with the power estimation. So the older flows like switching activity based and all those things are there are tools to use those waveforms to come up with the power estimation. But that needs your inputs, like you said, the tech node information and all, which one you are targeting, and based on that.
Hi, I wanted to ask, what are emulator platforms? Is it something like Vivado, or what do you use commercially?
Okay, so in market, there all these EDA vendors have their own platform. Like Synopsys has ZeBu, which was earlier emulation and verification engineering, Eve, and Synopsys acquired ZeBu. So they have their own platform, and each platform comes up with their upgradation, okay, in terms of speed and how much they can have the design or capacity wise. So then you have Cadence has the Z1, and so we have all the platforms. And sometimes when we use these emulator transactors, we are fixed to a platform. Otherwise, design-wise, no one stops us to put in any of this platform. We have VLSI from Mentor or Siemens. So all the platforms is available within ARM, and we use all the platforms. We try to, based on capacity available, and each project gets assigned to a particular platform. But when it comes to using an emulation transactor of PCI or something, we are fixed to a platform because we are using their emulator transactor, which will not work anywhere else. But if you take an IP, third-party IP from any vendor, like PCI from Cadence or somebody else, then IP can be used in synthesized in any of the emulator platform. So it's not very agnostic to emulator. But yeah, we have all the platform, and these are like defined in terms of the speed and the capacity, how much they can take it up, and in how many modules. So every emulator platform has their own way of categorizing. Okay, a design of these many million gates can fit into my one board, because my one board capacity. Ultimately, down the line, it's FPGA only, but it's baked in a pre-requirement fashion, where ultimately you can say, okay, my thing is fixed. It's not, the FPGA and emulation is little different. FPGA, you can tie multiple FPGA or connect multiple FPGAs, wire them to make a platform. Here, emulation, you are fixed. You can bake in the design into emulator, but how many modules of those standard sizes you are taking? So every time it comes, okay, next version of ZeBu, for example, in one module can fit in these many million gates, or it can run in this is the driver clock frequency. It can run up to, it can support up to. So all those, they have different knobs like fill rate. If you increase the fill rate like 80%, if you want to fill the logic in that, the compile might be challenging, the routing might be challenging. So those are the different things. But these are fixed platforms we are talking about in which we emulate the design.
Thank you.
So the third-party partners who are making their own ASIC, right?
Yeah.
So if they do not have these emulators and they want to go with normal simulations,
yeah.
So what do you suggest? Like, do you come up with certain set of test cases that they need to run on their SoC?
Okay, so this is so typically when you go to SoC and you want to do your software level validation with the full config and all. Generally, it is emulation technique is used. Simulation, when it goes to this level of design, it's very difficult. But there are simulation level SoC, the techniques which Arul was telling, a lot of techniques are used, like smaller config, you simulate more, you run more cycles, and bigger config.
No, my question is, it is already verified through emulation at your end.
Yeah.
And the third party, your partner, he's trying to use it as an integration. Like he just integrates it with several other IPs in the SoC.
Yeah.
So there, for them to basically get the confidence that their integration is proper.
Yeah.
Do you suggest? Do you come up with any certain test cases that they can simulate?
So this is the typical discussion we have with partner, correct? So when you verify at subsystem level, where you want us to focus on top of that when it comes to SoC. And what we want them to focus on after this is done is the different other components which they attach, focus verification on those data parts. Like suppose they have a different PCIe Express or different peripherals and different in-house accelerators where we don't know the traffic patterns. So either they say, okay, this is the accelerator we have connected and this is the traffic pattern. We can emulate that. But if we don't know, the use case based or what is sitting behind PCI, whether it's a storage or NVMe or something which we don't know, based on their use case, they can focus on those verification aspects. Techniques, what they use is up to them. In terms of methodology, it can be simulation, emulation, FPGA, it can be anything. But typically, what we have seen is partner have their SoC in their emulation or FPGA board. They have asked for us a particular config of a subsystem which is reduced in size or configured so that they can run their own softwares on that. So that software flavor we can't bring. So that's what we want them to focus on.
Thanks.
Yeah, typically in the emulation initial setup, what is the time spent on resolving the issues related to mapping your design onto FPGA? Is it smooth or you have to spend some time there?
Yeah, I would say very design dependent. If the complexity of design increases, like you're talking about bigger design like 128 core and in terms of so everything is stressed, correct? Emulation is also stressed in terms of compile efficiency, and even software is stressed because it's like 128 core boot. So emulation typically initially we have seen that it takes of a 128 core kind of design, it took a month for us to clean up the flow. So cleanup can be, initially compilation related issues, whether you are able to compile the design, what is the compile time, it ranges from 20 hours to 24 hours also, for a bigger design. And in that, how do you reduce the compile time? And another thing is what driver clock frequency you achieve or what frequency you are achieving. So play with that, and then how much design is bloating while you are trying to do that. So all this cleanup together, it typically takes initial 1.5 months. Then with that, you have this estimation of similar design, how much it will take. We extrapolate and see whether single chip is taking this much time, then multi-chip, how much it will take, and then try to prove it when actually you're compiling the design. So yeah, there are issues like compile time. There are issues like compile itself will throw a lot of errors. There are issues where a certain emulator might throw errors on certain constructs of the design because it doesn't support or it needs a next version of the emulator software to synthesize that construct. So synthesis related issue, compile time related issues, size related issues, bloating the design. And moving from when they cross the one board to other board,
the resource allocation also gets affected, correct? So if it is a 12 board design and we have 12 board in production and then we have another additional 12 board, if it goes from 12 to 13 board, we have to switch from one mode to the other mode in terms of regression. So considering all these things, the major challenge in emulation bring up is compiling the design, what feedback it has, the frequency achieved, and then the footprint, how it is handling with the footprint.
Okay, just one more question. If I understand correctly, the SVRIS tools drive the VIP, synthesizable VIPs ported on the FPGA. Am I correct?
No, not really. It does those VIP also, but majority it is the CPU's payload, correct? So you have these are instruction sets, correct? Put in the memory. So CPU is executing those instruction sets. As simple as that. Along with that, you need some synchronization between some IO traffic and then the CPU traffic. So RIS understands that, okay, suppose for example a producer consumer, correct? So RIS
Any further questions? Otherwise, I would like to invite all the speakers on the stage. We'd like to hand off memento. So the first one we'll give to Vikas Chandra.
Thank you.
Thank you.
Next we'll hand it off to Harul Suvasan. And the final one for Alok Sharma. Okay, thanks everyone for attending. Hopefully we learned something new, and I think it's time for lunch. It's right behind in the cafe, and we'll see you all at 1:30 for the next session. Okay, thank you. Thank you so much.
Thank you.
We have these boxes. Okay.
This room is busy.
At 1:30 there will be another session here.
So we take out.
Unless you want to attend here, you can stay here.
When does that finish?
It's 3 hours, so 1:30 to 4:30.
So I'll take it. Any suggestion where I can sit outside?
Anywhere. I mean, the cafe is all empty. Once the lunch is done, it's empty, or any of the.
Internet accessible to us?
I need to check on that. I can check on that.
Cool. Yeah.
Hello.